Now that we feel comfortable, hopefully, with probability, I want to talk to you about a specific model, and this is the binomial model. So in order to understand the binomial model, you have to understand what a Bernoulli trial is. So a Bernoulli trial, essentially you have two outcomes, success or failure. Now, that doesn't mean there's only two options. For instance, if I'm rolling a die and a success is rolling a 2, a failure is rolling a 1, a 3, a 4, a 5, or a 6. But again, there's only two options. Either I succeed or I fail. Each trial is independent. We've talked a lot about independence. And the probability of success is the same for each trial, and that is because they are independent trials. We call that probability of success P. So in my example here, where I win with a 2, I lose with everything else, this probability would be 1 out of 6. That would be P, which I of course would write as a decimal, but we'll keep it as a fraction for now. The probability of failure is also the same for each trial. Again, because it's independent, that value is 1 minus P, which of course makes sense because remember it has to add up to 1. So this would be 1, 2, 3, 4, 5 out of 6. That's Q. That's the probability of failure. I wouldn't have had to add all of those up. I could have just said, well, Q is 1 minus 1/6, and that of course is 5/6. So there's P, the probability of success, and Q, the probability of failure. So again, we've talked a lot about independence. Say I'm drawing marbles out of a bag containing 10 marbles. Are these independent? Obviously, no, they're not, because there's 10 marbles, and so that probability is going to change drastically if I take one marble out of the bag. What if I had a very large bag and I had 10,000 marbles and I'm just taking one of them out? Now, would I feel better about independence? Yeah, I would, because yes, although the probability will change a tiny little bit, it'll be so small that it'll be virtually insignificant. So again, 1 out of 10, yeah, that's a big deal. 1 out of 1,000, not such a big, or sorry, 10,000, not such a big deal. So even if events are dependent, like we have with the marbles, we can say that since our sample is smaller than 10% of the population, the trials are essentially independent enough. So we call that the 10% rule. So again, we're going to start talking more and more about conditions as we move into next week. So just keep in mind that this is one we'll hit again next week, the 10% rule, meaning that even though we've got dependent events, as long as our sample is at least or is less than 10% of the population, then we're okay. So let's look at our first example. So we have O negative blood can be given to anyone, universal donor, and is found in about 6% of people. If donors line up at random, what's the probability that 2 of the first 4 donors have O negative blood? So first we ask ourselves, are these Bernoulli trials? Well, yes, because success or failure. O negative, not O negative. Any of the other ones doesn't matter. Does it satisfy the 10% rule? Well, it's 4 people. So we're assuming that 4 out of, all of the blood donors, that yes, it's going to be less than 10% of all of the blood donors. Okay, so now that we know that yes, it meets that 10% condition or 10% rule, then let's talk about the sample space. The sample space are all of the ways, in this case, that we could have 2 O negative donors. So we could have the first 2 are O negative, the next 2 are not. We've got an O negative, a not, an O negative, a not, etc. So essentially I've listed all of the different ways that that could happen. There are 6 different ways for that to happen. Each of those ways has a probability of 0.06 to the second times 0.94 to the second. Now, before we talk anymore, where did I come up with that? Well, this one, success, remember that's O negative blood, that's the 0.06. This is also 0.06. This failure is 0.94, and this failure is 0.94. So there's 2 0.06s, and again, these are all events that I would be multiplying. So this one would be 0.06 times 0.06 times 0.94 times 0.94. What would this one be? Well, even though it's in a different order, I would still take 0.06 times 0.94 times 0.06 times 0.94. So instead of writing that out, which is ridiculous, we're saying, all right, each time I've got 2 successes and 2 failures, which is this large number. So all of the ways that that could happen is this 6 times, because 1, 2, 3, 4, 5, 6 times. So the probability of getting 2 O-negative donors is 6 times that value, which is basically 19%. Now, that's kind of a pain in the rear because I don't want to have to list out all of the different possibilities each time, because that would be a lot of work and I'm too lazy to do that. So we can instead use the number of combinations here and the number of trials or probability of each of those trials here. So we're going to put these two things together to essentially find the same thing. Now, before we actually use this to redo that question, let's look at what this means. N is the number of trials. So here we've got essentially 4. We've got 4 people standing in line. That would be N in our case. K is the number of successes. So remember we said out of those 4, 2 of them would be have O-negative blood. So this would be, in our case, 4 choose 2. Notice there's no fraction here. Don't put a fraction bar because that's very misleading and incorrect. Now, what do all these exclamation points mean? That just means factorial. So hopefully we know that this means factorial, and factorial means multiply starting at that number by each number below it all the way down to 1. So that would mean that this is 4 factorial over 2 factorial, and then 4 minus 2 factorial. So the long way, 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 4 minus 2, which is 2, 2 factorial is 2 times 1. Now, of course, we have calculators that will compute this for us, but it's important to kind of understand what's happening here. I can take out that 2 and that 1 to make my computations a little bit easier, and this might be important to you later on when these numbers are larger. So that would give me 4 times 3, which is 12, over 2 times 1, which is 2, and guess what number 6 is? Remember the 6 different ways that we could find the sample space, find 2 out of 4? That's this number right here. So instead of having to list them all, which can be incredibly cumbersome when you have a lot going on, this just gives us that value. Now, the probability of each combination is found by p to the k and q to the n minus k. So again, it's a lot of variables, but let's really think about what's happening. P is the probability of success. 0.06, which is the probability of success, to the k. So that's the number of successes. Number of successes, or probability of success squared, because we have 2 successes. And then q, which is the probability of failure, to the n minus k. Well, n is 4, k is 2, 4 minus 2 is 2. Now, this just means 2 successes, 2 failures, and again, we've got that 6, and so really it's going to be 6 times all of that, which is exactly what we did on the last page. So again, putting it all together, we're choosing n choose k times p to the k, q to the n minus k. That's going to give us our probability. The mean of the model, these are just things really to memorize. The mean of the model is taking n times p, and the standard deviation is the square root of npq. So let's take a look at how we might use these. Okay, try not to throw up when you look at this page. It's a lot of stuff that I've written out, but I really just wanted to show you step by step by step. Where did all of this come from? Well, this is that same example that I just went through with you step by step on the other page. The probability that our random variable is equal to 2, 2 of the first 4. So it's equal to 2. 4 choose 2, probability of success to the k, which is 2, probability of failure, which is 0.94, to the k minus n, n minus k, which is 4 minus 2. So again, I've got 0.6 squared, 0.94 squared, and then this is just me showing you again that yes, you can write all of this out, etc. So I've got 6 times 0.6 squared times 0.94 squared, and then that's the same probability I had before. Let's try one that we haven't done already. We're trying to find the probability that I roll 4 5s in 6 rolls of a standard die. So that's a lot of numbers. I've got 4, I've got 5, I've got 6, only 2 of them matter. 5s does not. So the 5s is just telling me that, hey, that's what I'm going to use to determine my probability. So the probability of a 5 is 1/6. Okay, the probability of not 5 is 5/6. So why is that important? Because P is the probability of success and Q is the probability of failure. So there's going to be my PQ right there. So I'm finding the probability that I roll 4 5s in 6 rolls, and then the mean and standard deviation. So we'll get to those in a second. So really what I want to do is I want to use that crazy formula that I had before, which says the probability that x is equal to x is equal to n choose k, and then p to the k and q to the n minus k. So let's look at it before I uncover all of the work. In this case, n would be 6 because there's 6 rolls, and 4 of them need to be 5s. What's P? P is the probability of success, which is 1/6. Now notice here, no fraction sign because it's a binomial coefficient, which is what all of those exclamation points gave us. This is 1/6, an actual fraction, to the how many? To the 4th power, because there's 4 successes. The probability of failure is 5/6, and how many times does that happen? Well, the 2 that are left over. 6 minus 4 is the 2 that are left over. So that's really all that we're going to do. So let's take a look. Again, I've got the probability that x equals 4. Oh, I forgot to put that over here, that x equals 4. 6 choose 4, 1/6 to the 4th, 5/6 to the 2nd. This part right here, I don't really need to see all of that work, because typically in my calculator, I'm going to just let my calculator figure that out, because we're trying to find the number of combinations. So in the calculator that I use, I'm going to find math and prob, which is probability, and then NCR, which is basically code for find the number of combinations. And so I would do 6C4, and that would tell me 15. So this part, not important to me. It's important that you understand where it came from. But essentially, that's telling me there's 15 different combinations of me being able to get 4 5s in 6 rolls. Then I'm just multiplying it out, and then this is my probability. Now, what's the mean and the standard deviation? Well, then I'm just using those formulas. So the formula for mean is n times p. N is 6 because there's 6 rolls. P is 1/6 because that's the probability of success. So that's 1. And standard deviation is the square root of NPQ. So n is 6, probability of success 1/6, failure 5/6, multiplied that all together, took the square root to get 0.913. Now, what does all that mean? Well, that means up here that the probability of rolling 4 5s in 6 rolls of the die is less than 1%, so it's 0.8% essentially. And we would expect to roll a 5 only 1 time in 6 rolls, which makes sense, with a standard deviation of 0.913. Here's a question for you to try on your own, so press pause, try all 3 parts of this question, and then press play to check your work. So here we have 30% of packaged bags of chips have a burnt chip in them. I don't like the burnt ones, but my sister-in-law loves them. So 30% have a burnt chip. Find first the probability that you'll have 2 bags with a burnt chip out of 5. So 2 out of 5. So again, if I'm using my N and K and all of that, I'm saying 5 choose 2. And remember, this part is just going to tell us the number of different ways that that can happen. And then the probability of success is 0.3, if you call burning your chips a success. So 0.3 squared, because 2 of them have burnt chips, and then 0.7, which would be the non-burnt chip bags. And out of the 5, of course, there's 3 of those, because these have to add up to 5. So the probability then is just me finding that value, which is 0.3087. So the probability that 2 out of 5 bags will have a burnt chip in them would be 30.87%. What's the expected number of bags with a burnt chip out of 5 bags? Well, of course, expected would just be the mean. So remember, expected means mean. 5 times 0.3 5 because there were 5 bags, 0.3 because that's P. And then this one doesn't ask for the standard deviation, so don't worry about it. The probability that 2 or less bags have a burnt chip in them. Well, this one's a little bit harder, and I'm going to show you how to do this nicely using technology a little bit later on. But for now, we would have to find 2 or less, which means I would have to find the probability that 0 bags did, the probability that 1 bag did, and the probability that 2 bags did. So I would have to do all 3 of those and add them together. So here, that's what I've done. Notice that I've written it as the probability that x is less than or equal to 2. I've found the first one, 5 choose 0, because 0 bags, 0.3 to the 0, 0.7 to the 5th. For 1 bag, it would be 5 choose 1, 0.3 to the 1st, 0.7 to the 4th. And for the last one, for 2 bags, it would be 5 choose 2 of 0.3 squared, 0.7 to the 3rd. And these are all the values that I came up with, and I added them up. Again, doing this by hand, not awesome, so we are going to show you how to use all of that in technology, but I think it's important for you to really get a grasp of it first before we let technology do the work.